Is gravity truly a fundamental force? Are black holes really cosmic dead ends? Or are we missing something bigger? What if gravity is just an illusion, and black holes, those mysterious, all-consuming giants, are not destroyers of information, but processors of it? Welcome to a new perspective, one where space, time, matter, and even the universe itself may all be emergent from information. Section 1. The traditional view. For over a century, gravity has held its place as one of the cornerstones of physics. It curves space-time, binds galaxies, and keeps our feet on the ground. And black holes? They're the most extreme example of gravity in action. Regions where the pull is so intense that nothing, not even light, can escape. Traditional physics tells us that once something crosses a black hole's event horizon, it's gone forever, lost to the singularity, where physics as we know it breaks down. Time itself slows dramatically near this region, and all known laws collapse into mathematical chaos. But maybe that's just part of the story. Section 2. The puzzle of unification. One of the biggest mysteries in physics is this: why can't gravity be unified with the other fundamental forces? Electromagnetism and the weak nuclear force unify into the electroweak force at high energies. Even the strong force fits into the puzzle, at least in theory. But gravity? It stands apart. General relativity explains gravity on massive scales beautifully. Quantum mechanics, meanwhile, governs the tiny world of particles. But these two frameworks refuse to play nicely together, which is why physicists have started to explore a radical idea. What if gravity isn't fundamental at all? Section 3. Emergent gravity. In 2011, Dutch physicist Erik Verlinde proposed something fascinating. Gravity might be an emergent phenomenon. Think about temperature. It's not fundamental, it emerges from the collective behavior of molecules. In the same way, Verlinde suggests that gravity emerges from the way information is distributed in the universe. Imagine this: you walk into a room and see an ice cube melting. Is there some magical, melting force at work? No, it's just the system moving toward higher entropy, a more probable state. Gravity, Verlinde argues, works the same way. It's not a force pulling objects together, it's an entropic response to how information is arranged. And that shift in information? That's what creates the illusion of gravitational force. This idea doesn't just explain gravity, it may even replace the need for dark matter entirely. Section 4. Spacetime as information. Now, let's go deeper. How can spacetime itself be linked to quantum entanglement? Some physicists suggest it may emerge from quantum entanglement. In this view, the universe is woven together by invisible threads of entangled information. These threads form the fabric of space. And when mass or energy disturbs this fabric, it changes the pattern of entanglement, which we experience as curved spacetime. Space and time might just be consequences of how quantum information is organized. It's a radical shift. Instead of viewing spacetime as a cosmic stage, it becomes the performance itself, a constantly shifting tapestry of entangled data. Section 5. Black holes, the ultimate computers. And here's where black holes come back into the picture. We used to think they destroy everything they consume, but thanks to Stephen Hawking and Jacob Bekenstein, we now know black holes have temperature and entropy. And their entropy? It scales not with their volume, but with their surface area, the event horizon. This led to the holographic principle, the idea that a 3D volume of space can be completely described by data encoded on a 2D boundary. So what does that mean for black holes? It means they don't destroy information, they scramble it, store it, and maybe even release it back into the universe. Physicist Seth Lloyd took this further. He proposed that black holes act like quantum computers, processing information at the maximum rate allowed by physics. They're not cosmic garbage disposals. They're processors. Black holes compute. Section 6. Cosmic computation. When black holes emit Hawking radiation, they may be releasing that scrambled information, bit by bit. It's not random, it's computation. The universe itself might function like a quantum computer, constantly evolving through logical transformations of data. Space, time, matter, they could all be outputs, not inputs. In this view, reality isn't made of particles. It's made of information, and black holes are the thinking nodes in this great cosmic network. Section 7. Penrose and the cycles of time. But what happens when the universe dies? Enter Roger Penrose and his theory of conformal cyclic cosmology. According to Penrose, the universe doesn't end, it resets. Each cycle, or eon, begins with a big bang, and ends when all mass decays and only radiation remains. As black holes evaporate, they release the last traces of information. That radiation is then stretched, compressed, and transformed, until it triggers the next big bang. In this way, black holes become cosmic messengers, carrying information from one universe to the next. Even more bizarrely, quantum fluctuations might birth entirely new baby universes, seeded with the data black holes released. In that sense, black holes may be the architects of new realities. Thanks for watching. If you enjoyed this deep dive into the edges of physics and philosophy, consider liking, subscribing and letting us know what you think. Can black holes think? Can the universe compute itself?